All right, today the idea of using effective potentials again. We did this for the very simplest polar coordinates. We're going to take on some slightly more advanced stuff after we review the basic idea of finding systems that have several different frequencies going on at once. We'll just have two in this case. And the idea is to find initial conditions or situations where those frequencies can be rational ratios, which means that the system will actually repeat perfectly after a while. It can be a long while, but it's interesting to see this kind of classical behavior, because a system that is set that way will exhibit some interesting quantum behavior often. We'll take on just a simple oscillation associated with polar coordinates, and then like to do a 2D spherical pendulum, or what we call bowling. And if you wouldn't mind handing me that thing called the eyeball back there. It's up by the, yeah, thank you, Valley. That's the system we're going to use this on. It's an interesting thing I got for a Christmas present. I'll get it out of its box so that we can start using it when this comes up. So this is one of the things we'll do early on, and it has several balls in there that make orbits, and the idea will be to see if we can show that. Okay. After this, I'd like to go through ruler and compass construction of the cycloid, which I will give us an assignment, along with some problems that are connected to both the geometry and the dynamics. The cycloid is famous, most famous for being a brachistochrone, that is the quickest path, the shortest time, and also as having what we've looked at already a little bit, equal time. That is a frequency that doesn't depend on amplitude like the ordinary pendulum. So the cycloid pendulum, or cycloidulum, which is the name of the app that we'll look at again, is a very good thing to know about, and we're going to go into the algebra of that, and then that will prepare you for a problem on that. The cycloidic geometry of flying levers, that's something that everyone should know, and this will bring us down to earth. And I hope this is a fairly short, a shorter bunch of algebra today. I want to show a practical pool hall application of that is kind of amusing. So let's go ahead and get started with just the basic idea using the two-dimensional polar coordinates before we get into the spherical coordinates. Remember that we had a Hamiltonian that could be written either in terms of the covariant metric and the velocities, which involve the time derivative, the little dots on top there, of the q's, the queer coordinates. In this case, the queer coordinates aren't so queer. They're just the cylindrical radius given by rho, and the azimuthal polar angle given by phi, and then we have a third dimension here, z, just along for the ride. We're mostly interested in the curvilinear behavior that's from those two terms. Then the alternative representation of the Hamiltonian, which is the one that's formally correct. They are both numerically correct, but this one is formally correct in the sense that it's using the momenta, the canonical momentum, or the covariant, so what name we've been giving it because of the Riemannian Christoffel equations that involve the full covariant mechanics. So we have here covariant as opposed to contravariant variables, and that means that we have covariant variables, we have to have a contravariant a dynamic metric tensor or matrix, just the opposite of this description here, which would be okay in the Lagrangian world, but we're taking advantage of symmetry here in this particular thing. So the Hamiltonian world is a good place to start. And if the potential that goes with this is all kinetic stuff here, if the potential that goes with this particular cylindrical system, if this thing is just a function of radius and not of the polar angle, then we have a constant of motion in addition to the Hamiltonian. And if that Hamiltonian or Lagrangian has no explicit dependence on the polar angle, then the momentum that goes with that angle phi, namely P covariant phi component, is definitely a constant, which we'll just label by the Greek letter mu as we work with this. So we've seen a little bit of this already. It turns out that H has no explicit z dependence, so the z momenta also, the momenta goes with it, which is just m times of z velocity. Nothing fancy there, but it's interesting to have that because whatever's going on in the xy plane, that is in the rho phi plane, can have also a drift momentum, that is velocity, coming out of the board, and nothing will change as far as the view, just using these two coordinates. In other words, projection of the motion that might be coming out of the board will look the same on that original plane. Okay, so here is the Hamiltonian again now with the constant mu stuck in there for what used to be a dynamic variable. And idea is that this is an effective potential due to dynamic, it's effective dynamic potential. There's the whole potential, which we call the total effective potential for this system. Now we're going to go ahead and let k equal 0 so we don't have to worry about what's going on out of the plane here, and just treat this particular very simple Hamiltonian, which involves the radial momenta and then an effective potential for the radial coordinate. So it's back to being a two-dimensional system, 2 degrees of freedom, really one dimension, 2 phase space dimensions. So effective potential has this inverse rho squared, which is positive, so that's a steep curve that is added to, the 1 over rho squared is added to whatever potential we have, whatever function v is of rho is having this thing added to it. So what we're going to be doing is looking at, first of all, how does the phi dot, that's the angular velocity in the plane, behave as the variable, radial variable rho changes. And you can see that as the variable rho gets small, and this is the mu over rho squared times the mass, the angular velocity has to increase inverse square of the radial distance. So obviously this would be infinite if I were to take rho to be 0 while having an angular momentum mu that was supposed to be constant. So the centrifugal barrier is basically keeping that from happening. It's preventing the catastrophe of getting right through the origin. You will never go through the origin. That means in quantum mechanics, the wave function had better be 0 at the origin if you have any quanta of angular momentum at all. Now the radial derivative, that is rho dot Hamilton equation, that's partial h with respect to the momenta, and in this case it's very simple. It's just a rho, the rho momentum, covariant momentum divided by the mass. That's radial velocity. And we can go ahead and put that, solve for that rho dot, and or solve for the rho p over m, and we get plus or minus this energy minus the effective potential at every value of the radius. So this is telling us what the radial momentum is doing, and the effective potential, of course, is this combination right here. Okay, now, having done that, having gotten the time derivative, then if need be, you can go ahead and usually numerically evaluate an integral with respect to the radius from any particular initial radius to whatever final radius, and that would give you the time that it takes to execute that particular motion, that is the travel time going from radius 0 to rho 1, presumably given by this integral. The trouble is it's multi-valued, so you have to be careful about that. But anyway, that travel time is given sometimes analytically, but more often than not, it's a numerical integral that you would have to do. Now, what we're going to be concerned with are things that you can do analytically for almost all of the problems that involve anharmonic potentials. And the idea is to find a region or regions where the derivative of the effective potential, that is the dynamic part plus whatever other forces we have in this that are described by potential, to be zero. That is some region where the topography lines for the effective potential have some kind of, well, let's say a resting place where there's no gradient. And the most common situation is just the origin of, say, a harmonic oscillator. But the other alternative that's very often encountered is in a flat region that's unstable. Now, this one would be unstable even if this curvature was into the board. That is, if the thing was, this was a maximum, then obviously the slightest disturbance from that flat would get it started moving, and it would go away exponentially, just like we talked about in the case of the Trebuchet model. But we're assuming here that this is a bowl coming out of the board with energy plotted this way, so that the energy is higher and higher and higher, just like a harmonic oscillator. Or an anharmonic oscillator doesn't have to be quadratic. It can be some other curve, and we'll get plenty of examples of that fairly shortly. But this is the other alternative that you could have that's very much like the situation we had with the Trebuchet model. There were situations where like in the phase space of the pendulum, where it went up on one side and went down on the other side, so there was that place where the pendulum was perched on top, and this is a unstable singularity, if you will, in the phase space. So again, we're talking about 1 degree of coordinate freedom here, so these curves are easy to make, and the momentum is the transverse dimension in the phase space. So we'll take a look at a couple of examples of that as we go along here. Now, once you have this, a stable minimum, And let's suppose that you evaluate the second derivative and find that it's a healthy singularity, that is a singularity that is stable in the sense that you can orbit around it. Then the job will be to calculate the actual numerical value of that, estimate the frequency that this system would have. That is, what you'd like to do is just look at the first non-zero term in the Taylor series for the effective potential around a stability point. And it's assumed now that you're really talking about the location at or very near that stable point, where the first Taylor term, that is the one that's linear in rho minus this magic point or stable point, is first power. And we're assuming that the coefficient of that has been made 0 by solving this equation right there. That is the minimum finder. So what we're going to come up with is an effective spring constant at the stable point. Okay, it's case K effective for the pseudo-oscillator, pseudo-harmonic oscillator, pseudo because it has terms that are waiting to destroy all this, but we're presuming that we're close enough to rho stable that they can be ignored. Then this constant right here, the curvature of that will, if divided by the mass and then a square root taken, so there's the formula in terms of the derivative of what we're looking for is the frequency for that particular coordinate. Now we'll have a situation today where we'll have two coordinates that each have frequencies that are different, and it's the job to figure out what to do about that, what can happen with those two, what sort of normal modes exist, for example, in a system like that. So these small oscillation orbits may be closed orbits if the ratio for, say, one variable rate, that is here phi dot, is the frequency that goes with the radius, I'm sorry, with the polar angle, and then this one right here, omega, is the one that goes with the radius in and out. So it's possible to get a closed orbit for any, maybe, possible, practical, to get an orbit like that with an integer here and an integer there. And like just very briefly to take a look at sort of a picture of the, well, here are the two most famous possibilities where both of these integers are 1, the one-to-one orbit, and this is where I have an oscillation back and forth in the rho direction, in the radial direction, that has exactly the same frequency as the oscillation around. That's the phi dimension of this, whatever object this is. And this is a very general sort of discussion that one has to have with all sorts of classical mechanical systems, that exists some sort of stability. That in the neighborhood of that stability, you can have, well, any integer set here. And I'm going to go ahead and try to follow the lectures here on the other computer. It'll drive Al crazy on the camera because we'll have to bounce back and forth a little bit. But just to get an idea of what I'm talking about here, let me just bring it up to this point and go one step further. And I think this will, for some reason that one is been pulled out. That's what happened. Put the USB back into the slot there and hope that this keyboard works so I don't have to go down and bend over every time. So we've gone through here just the Hamiltonian centrifugal barrier and some of the geometrical properties of it. But here is a little bit more of a map of the possibilities that we get when we have more than just integers 1 and 0. Obviously you can have an integer 0 by just not activating, but if you do that, you're just stuck on a curve in there that is going around some particular stable radius. So m to n ratios, where I'm plotting the m this way, and the n is this way, 1, 2, 3. So all the possibilities up to 5 by 5, and then there's a 6 by 5 there. And you can see basically that there are two kinds of symmetry for these orbits. There's a cyclic symmetry associated with the, if we just keep the n equal to 1, that's the n that's associated with the radial behavior, and look at different values of m, the symmetry is pretty obvious. You're just going from what we would call C1 symmetry to C2, a cyclic 2, cyclic 3, cyclic 4, cyclic 5, and so on, assuming that we can have these orbits without getting too cranked up and fly out of the approximations of small oscillation that we're talking about here. But it's also interesting to see then what you would have if I had increased the symmetry associated with sort of looking at this thing from the inside. That is, the inside symmetry associated with looking across the cross-section here. You see the n fold. So I've got some number of dots going around. This is very obvious, you see, symmetry. And as you go, across this thing, the internal symmetry doesn't destroy it very much. You can obviously see that that's a 5-fold symmetry. Now this would have been a 6-fold symmetry, except it's 6 to 2, so you have to take the the lowest common multiple, or you have to reduce the fraction as you get by dividing these things. When you do that, you get 3 in this case. So that's the sort of little bit of number theory that these things are going to play us with. And you'll notice that as I go down the diagonal here, it basically looks the same every time. It's just going faster. But both of them are going equally faster, so you don't see any difference in the coordinate trajectories of the thing. But some of these are sort of hard to see because I'm looking at it from the top. I need to look inside there and see that this thing has a 3-fold symmetry looking around sort of like this is a torus, and I have symmetry around the torus that I can see very easily, but then I have to look this way, going around in the angle there to see the other one. So this is a, kind of a neat topology and numerical exercise. Now, after you find that these things are possible in a system, and as you're going to see with a couple of problems that I give you, very often you're just restricted to a few of these, and you'll see why that is as you do each of these problems. But one we're going to do today with Mr. Eyeball there is restricted to essentially 2, the first 2 that we talked about here. And we have really only talked mostly in this class that we're doing these 2-dimensional problems, such as the sophomore physics Earth. We had only 2 possibilities with the sophomore physics Earth. There was 1-to-1 and 2-to-1. 1-to-1, well, 2-to-1 if it was the right shape, and this is not the right shape. This is not an ellipse. And Really, neither is that. But if it were an ellipse, it would be our old friend, the two-dimensional isotropic harmonic oscillator. This is very anisotropic, but still having the same topology. Now, that's inside the Earth if it were an ellipse. The problems that you've just finished now have something to do with that. Outside the Earth, we haven't talked much about the Coulomb orbits that live outside of the Earth. They're ellipses too, and they have a 1-to-1 ratio. Okay. Now, if you were to have a 1-to-2 as opposed to 2-to-1, you get a very weird thing. And then if you somehow manage to have both of them the same, well, that's the diagonal of these diagrams, and they're going to more or less look the same as far as symmetry goes. Okay, so this is a part of mechanics that doesn't get a lot of discussion in the older books, but people that do semi-classical mechanics, that's mechanics that involves a large enough quanta that you can treat the quantum system sort of as half classical. That's the semi-quantum is what it really is, but semi-classical field of physics has really grown because it's the most practical way to deal with things like molecules and even nuclei and maybe graphene and things like that. But these are, you know, speculating whether that kind of looking at things, first fully classical like we're doing here, but then later on looking more carefully to see how it marries with the quantum complications of having waves determine everything. Now, we're going to talk about the two cases, 1-to-1 and 2-to-1, with a real example, namely the eyeball. But before I do that, I should maybe zero in on this little picture down here. And that is the picture that you get when some sort of very nice ratio has been found, and then you just alter a parameter or alter an initial condition or do something so that that ratio changes. And that will take each of these and begin processing them. They will not quite follow that path. And I can give you some animations here that will to maybe give you some feeling for what it is I'm talking about there. But let's just take a close look at this, where we're considering ratios of the frequency for the radius, rho, and the frequency for the stuff going around. Okay, so we're talking about the frequency for the radius, which is the oscillation back and forth here, and then the frequency for the phi, which is the oscillation here, the phi oscillation, the n the sort of behavior has a 4 on it. That means the radial motion is 4 times the motion going around the azimuth. In any case, pick a value of something that's 1, okay, where the ratio of those two is 1. Come back to either this picture here, there's the 1-to-1, or we've got it here, it's up at the top. So when that ratio is 1-to-1, okay, you have some kind of closed orbit, the red thing, there. Now, if it's just below 1, then somebody's slow. Okay, if this is just below 1, that means that the radial oscillation is just a little bit slower than the phi. So every time it goes around, it comes up a little late, and that makes it do what's called prograde precession. That is, the actual object, this little loop here, will appear to precess in a that means with the direction of the actual motion of the point in this graph. Okay. Now, when you're just the other way, if you're just a little above 1, say 1.01 or something like that, okay, you get a retrograde precession of nodes, okay? And so the thing's showing up here early, at least if this is greater than 1, so radius is a little bit faster than the phi, but they're still pretty close, ratio of 1.01, say. But each time you can see that it's showing up, the row is showing up early. That means it's showing up on the downside of the direction. Therefore, the precession will be retrograde. The precession will actually move opposite. The orbit is, everything's going around this way, but the whole thing will precess oppositely to the actual motion. Then, the next stop may be 2 to 1, okay? In other words, and we're going to have this with this eyeball, we're going to be able to go from this situation almost to this one. We won't be able to, as you'll see for that particular physics, go above it and take any of the others here, but we'll be able to get, pretty close to 2. So if we could get to 2, then it would be this case right here, the oscillation that we're familiar with inside the Earth, but not necessarily an elliptical curve. And if you're just below that, if you're just below 2, okay, that means if you're just below the situation where the radial oscillation is not quite 2 times the angular oscillation, then you're going to have a situation where it's prograde. So when you're deficient in the motion, you see it's prograde, just like it was over here. If you could get past that point, you'd get retrograde again. But what we're going to actually see with the eyeball is a prograde precession of nodes. Okay, well that's saying a lot about this stuff that you may not follow. So it's one of these things that you just have to play with. And we will play with it a little bit fairly shortly. Okay, I'm going to move on here. There's the whole story. And actually look at the system, the bowling. We're throwing with balls inside a ball. This guy right here. Spherical pendulum is another name for this. We've been talking about, and we'll show remind ourselves of the dynamics of just a plane pendulum. It can go, all the way around. This one, with any angular momentum, is not going to be able to go all the way around. You see, there's a centrifugal barrier on this axis. You see, it isn't going to be able to go through the north-south pole either. So it's going to be confined to some sort of region.
Dr. Harter?
You see, that is away from those poles.
So this problem, the ball will have a symmetry about 5, right? Because
yes,
the gravitational potential energy would be mgr cosine theta.
We're definitely going to have a gravity potential here. If you don't have a gravity potential, then the ball has to follow a geodesic of that thing, which, as you know, is a great circle. But it can be anywhere. Our thing we're going to do is a lot more complicated than that.
So which means in this case, if we choose to write the Lagrangian, the kinetic energy would be half mv squared, but v squared written in spherical polar coordinates. V would be mgr cosine theta, and then we use the equation of motion.
Well, you're right, it has to be 1/2 mv squared, but we have to put that v squared in the queer coordinates.
Let's forget.
Do the spherical coordinates. Okay? And the spherical coordinates, I mean, you could do cylindrical and then play games with a constraint that, there's all kinds of crazy stuff that you can do. And we're going to talk about that in the next lecture, all the crazy ways that you can handle constraints.
And one
besides the ones we've been doing, which is to match the coordinates with the object. Yeah.
My last question is, in this problem we have 2 degrees of freedom, right? R and theta, because
yeah, we used to have 3, but we're going to be constrained in radius. So no radial oscillation at all. And that can be achieved with this thing as long as you've got enough speed to stay on the surface.
Oh, okay. Yeah, R doesn't change.
You see?
So just theta is the only degree of freedom.
And the other thing is, we're going to have balls that are so small, you have to worry about their rotational motion. Okay, so they could just be sliding points. So that's an idealization for the eyeball, right? Because it does have BBs in there, but they're very well-behaved BBs.
Oh, but even if the ball rotates, like if I have a tennis ball or something like that, where I cannot ignore its rotational motion. So even if I assume that the ball rotates with say uniform angular velocity omega, that would be included in the expression for the kinetic energy of the ball, but it would not be reflected in the equations of motion, right? Because omega doesn't change, so nothing changes.
No, we're not trying to be as complicated as we were with the mechanical cyclotron, right? In the case of the mechanical cyclotron, we're getting all of our funny motion due to the inertia of the ball on the table, right? Now, if the table was a sphere, that's a really interesting. I mean, I actually tried to build. I actually put that thing on the table there with a parabola, and it does some interesting things. But you know, we're thinking about how we engineer something like that. I think with the new ability to literally print mechanical objects, that the possibility for building, this thing with a fair-sized ball in there is well within the range, and that opens up a lot of classical mechanics. So the future will have a lot more to offer than just the eyeball. But we've got enough to deal with right now. So let's get the algebra out of the way, and then we'll talk about the physics. Jacobian matrices and determinants for polar coordinates. I'm going through this rather rapidly because I believe I have assigned you a problem to do this. So do your push-ups without having somebody help you. When you go to do that problem, pretend it's a qualifying exam like I've warned you, or I've suggested that you practice. This is training, right? So don't go until you get stuck and then you go back. But if you've at least tried, to get the right answer, you've already, built some muscle up here, right? And then finally say, oh, damn it, I can't go. But then you'll remember what you did wrong, right? At least you'll remember what you did wrong if you work on the thing for at least a couple hours or so, maybe a couple of days is what it should be, to really make it stick in there. And then you go and look at the answer. Well, if you work on it for days, you guys should be able to get it, right? But suppose we have a harder problem. It takes 2 days to figure out what the hell to do. And then you go and look. At least you remember what it was that stopped you, right? Okay, so by the way, the cylindrical thing is had as a subset of this one, and that's nice to have. Then here's the covariant metric, which we get by looking at the covariant vectors that are in the columns of this matrix, this guy, and this guy, and doing their scalar products. And they are orthogonal to each other, so this is not a fully engaged GCC. This is an OCC. So the metric tensor matrix, whatever you want to call it, is diagonal. We're just going to have three things. Old grrr here, GRR, okay, and then G theta theta and G phi. Phi is the most complicated one, an inverse r squared sine squared theta. This is just an inverse r squared, the same as we got in cylindrical or polar coordinates. So that's the thing that builds our Lagrangian form. We use the covariant to build our Lagrangian forms. We use the contravariant to build our Hamiltonian. Okay? So the Hamiltonian is over here. This is a Lagrangian form of kinetic energy. Just kinetic energy. Potential is fairly easily put on here. It's just the cosine of theta, the projection of the gravity force onto the sphere, which is a circle at any azimuthal direction. But we have a fully active theta and phi. We do not throw away anything here quite yet. We do, however, have the advantage of at least mitigating one of these, the spherical coordinates with constant r, implies the conservation of azimuthal momentum. In this case, there are no bumps in this thing around the phi direction. And the theta direction would be a symmetry 2 if I didn't have gravity. But I do have gravity. Gravity is straight up the z-axis here. And we've set the polar coordinates so that that is the polar axis that is at work here. We still have cylindrical symmetry around the phi direction, the azimuthal direction that is perpendicular to the z-axis. So this particular canonical momentum, and now it has, you see, a more engaged form. It isn't just mr squared phi dot, it's mr squared sine squared theta. Well, that's the effective radius. This is the effective inertia for a particular value of theta. But we're going to be changing theta, so we can't make too much use of that observation. But still, that's the exact result there that we're going to make use of. Now, I should remind you that the covariant momentum is usually defined as a triple equal sign, the partial of the Lagrangian with respect to phi dot. But remember, the potential can't have any phi dot dependence, can't have any velocity dependence at all for any of these coordinates. So that will always be the partial derivative of t with respect to phi dot, which is what we've written here. Okay, well, the rest of the Hamiltonian total energy has got these terms, okay? And we don't have a radial term. We just have the theta term, theta dot squared in. We actually have to go ahead and write that thing. Let's see if I've done it correctly here. I have done something a little weird there. I should have made a p theta dot squared there, but aside from that little screw up, I think we've got everything we need. Let's see if there's anything else I should say about this. Anyway, I'm going to define some coefficients here. I'm going to try to write this thing just alpha, delta, and gamma coefficients, where alpha is just the mr squared, that's a constant. The delta is, looks like not a constant, it's got p phi, but we've already said p phi is a constant. So that's what we're going to do. We're just going to call delta the p phi squared over 2mr squared. And then that delta sits over something that is varying. Theta is the main variable that's left after we take out the angular momentum. So we're back to having a two-dimensional system with really 1 degree of freedom now that we've made it symmetric and not having angular momentum change at all. P phi cannot change at all. And then finally, gamma will just be the thing mgr that is the coefficient of cosine of theta to give us the effect of gravity that any pendulum would have. Okay, anything I'm missing there? I think that goes. So let's put this all at the top here, and we're exposing here theta dot squared. Now we forget about the formalism that's associated with having a Hamiltonian. That's what caused me to write that thing sort of prematurely. But this is indeed what I want. I want theta dot. This is the velocity associated with the theta coordinate, which is the latitude of this globe, and the azimuth, the longitude stuff has all been subsumed now that the longitudinal momentum p phi is constant. So again, here are the three constants that we're going to be working with, and of course the energy, which was originally the value of the Hamiltonian, is time constant as well. So what we need to do is find an equilibrium point for a stable orbit, given these constants here. Now the main constant that's going to affect that is this one. This is just the same all the time, but this one depends on how much azimuthal momentum you've allowed this thing to have. So that little part right there is, you know, the main driver for all of the physics here. This is always the same. Okay? So we have to differentiate this thing with respect to theta and set it equal to 0. Find what are the values that would give this. So we're setting this thing right here equal to 0. So it's a fight between in order to figure out what theta is stable, we have a fight here between the gravity wants to pull the thing all the way to the bottom and the centrifugal barrier that wants to, you know, float it, not keep it from going to the bottom. If, of course, P phi, the azimuthal momentum, is 0, this is out of here and I just have the usual situation, and then I can go to the bottom. I have an ordinary pendulum, and that's the driving force. But this is more complicated. The driving force is working against, or in some sort of way, with the centrifugal barrier. And this particular moment where they are perfectly balanced will lead to an orbit that holds its theta all the way around the z-axis, that is, at a constant value of theta, constant latitude. So the small oscillation frequency near equilibrium is what we're interested in, but first we have to find that equilibrium value. And when we take the second derivative of this thing to evaluate that frequency and divide by the inertia that's associated with that particular theta. So this is solving that thing right there. 0 is equal to this thing phi dot squared, and then this thing sine theta. There's gravity, there's the, shall we say, centripetal forces trying to pull the thing up the sphere. And we end up here with a phi equilibrium that is just minus g over r cosine equilibrium value. Whatever that equilibrium value is, we're going to make use of that. Now, let's see if there's anything I've left out here. Polar libration frequency is what we're after. It's going to be related to the azimuthal frequency here. Now I just have a square on that thing right there. I have to get rid of that.
What is polar angle librational frequency?
That's kind of a name that you give to, you know, and particularly when a thing is really going fast, so that it's up near the equator, right? And so it's librating, right? Now, of course, it's going around like mad, right? But if you could ride with it, you'd see it oscillating, right? And we're after that, right? So we're going to compare that frequency with the whole orbit frequency around the azimuthal coordinate phi. Okay, that's the main job here, to get a diagram like we took, you know, these M to N diagrams. Okay, so let's do that derivative. We need another derivative. We've got the one to get the stability. Here's the second derivative, okay, of this thing. Talking about V effective here, okay, this guy, right? So we end up, of course, we have a couple of terms. We have a sine cube here and a sine fourth there. It's a little bit complicated, so lots of room for making all sorts of mistakes, which I hope by this time I'm not making. We've got a certain value for the gravity, a certain value for this delta that involves the quantum of angular momentum for phi, okay? And it comes out not too complicated. It comes out looking like that. That's not bad. Okay, it's nice cosine squared of theta dependence with the phi dot squared right there. And then the gravity is just multiplying cosine, as it has been everywhere here. So the main stuff that's coming from that derivative is right there. So at equilibrium, when I put in the actual value that I get for phi dot, stick that in, it comes out rather nice. That is, this derivative here is almost, except for this thing right here, like the phi dot squared. Now I have to divide this thing by the inertia, and I do that fairly easily, and I get a ratio between the equilibrium value for the theta libration ratioed with the around ratio. Now this is squared. These both are squared. So I have a 1 plus cosine squared theta of the equilibrium theta, whatever that is. And the faster you're going around, the further up, but never quite reaching the equator, you get. Unless you turn the gravity off, then you can go anywhere with a great circle orbit. But you're trying to approach a great circle orbit as you go up. Okay? Now at the bottom, theta equal pi, okay? That's where cosine is, if you're approaching the bottom, remember you can't get to the bottom, but approaching the bottom, the cosine is approaching 1, okay? So you're getting 4 for that squared frequency ratio. Square root of 4 is 2, so it's approaching the 2 to 1. That's the cool thing about the eyeball, is that its orbits are very nearly closed. And the closer you can get to the bottom, the less they'll precess. But remember we said they're going to do prograde precession of nodes, so that's the thing to check. Then as you get further up, where your oscillations is back and forth with quite a variation in theta, the libration becomes a major part of the motion, you're going to lose 2 and start going for 1. And then what's really neat is as you approach the equator, that is way out to as near the equator as you can get by whatever speed you can crank that thing up to, you'll notice that it starts to settle in on our Coulomb-like orbit, which has a ratio of 1 to 1, the very upper left-hand corner of the matrix of possible ratios, you see. But this is what it starts with. Now, how this is going to show on the camera, I don't know, but I can hold it up in the light here and just get the thing rotating and see if you can see the precession. It's a little bit hard to do, but the best thing for you to do, since you're in the classroom, there it's going. Now it's precessing. And you really have to look down on the top of it to see that. But what's nice is all the balls are doing it. There's 7 balls in there, and they're all doing it. See that precession? Now you just have to look at it from the top and see that it is indeed a prograde. It's going, if I'm making the balls go that way, then it's precessing that way. So this is, you know, a really neat little, you know, this thing was what, $4.95 at Dark Star Visual, one of these, you know, novelty items around town. Now there's a nice precession right there. You see it's about halfway to the equator when it's doing that one. Okay, so something to play with after class. And of course you can do the experiment at home if you've got bowls that are, you know, more or less spherical. Most bowls aren't spherical, so you'll get other ratios that are possible, and that's an interesting problem in itself. Okay, so the ratio is between 2 and 1, usually irrational, non-closed orbit. That means one that's prograde precessing. But you could obviously look for rational fractions between 2 and 1, where you would get closed orbits if you're really doing this on a computer, where to make it ideal. And remember, 2 to 1 is like the 2D IHO, you know, isotropic harmonic oscillator, inside the sophomore physics Earth with the neutron starlet. The 1 to 1 is, like everyone knows, Coulomb orbits outside of a spherical mass potential. Okay, well, at this point we're going to break and go back and look a little bit at the cycloid. And this time I want to show you something I would ask you to do by ruler and compass when the problem set for this comes up on Thursday for next week. What we're doing here is an attempt to show the irrational part of the cycloid on one dimension and then have the angular part be rational. In other words, pi is an irrational number. It's not 3, as it says in 2 or 3 places in the Bible. It is 3.14159. We're dealing with about 2-figure or maybe 3-figure accuracy at the best on a plot like this. So 3.14 is really all you need to know. But once you do that, then you can make a decent cycloid. And what you do, as it says here, is the radius is plotted as an irrational number that is just plotted on the graph. We're not claiming to be able to square the circle and have a geometrical way to plot pi, although there are such things that are approximate. We're just going to plot it. This is an engineering sort of ruler and compass construction. And it's this length right here, 0.955, which is the ratio of 3 to pi, that keeps showing up. Multiples of that are showing up here. 3 over 2 pi, then here's 3 over pi, here's 2 times 3 over pi, here's 3 times 3 over pi, and 4 times 3 over pi. So each of these numbers get irrationalized on this axis. But once you set those things, then you just draw horizontal lines off of that, and the cycloid construction, what you'll see, is quite nice. Now I'm going to only do it with a precision of pi over 6. I'm going to ask you to do pi over 12. In other words, do a full clock. It's already there, so it isn't going to be too hard to add that extra precision. But basically what we're going to do is, by making this irrationality be on this axis, then this length is taken care of. So rolling by a rational angle, which we can easily make a construction for that, we can easily 12-sect the circle into a clock like we did for the phasors. The diameter here, 2r equals 6 over pi equal 1.91, is the irrational part of it, but we're going to be able to roll out. We're going to imagine the circle here rolls. This particular one rolls from the left toward the right, okay? And it's rolling on the very top line here, which I call the y equal 3.82 ceiling. So this is a ball rolling on the ceiling, okay? And what it's doing, it's starting here at x equal 6/2. Okay, that's in these units down here. Here are the units: 6/2, 5/2, 4/2, 3/2, 2, that represent an angle that is, in this case, pi, 5 pi over 6, 2 pi over 3, and so on. That's the, here's pi over 6, okay? And I get that very easily by just moving the circle over to the next division here, the 5, and then looking where it intersects with the pi over 6. So I can immediately draw a pi over 6 sector of this pi, okay? And I've got a start of a cycloid right there. See, those are the first 2 points. Now there's obviously, you're going to have to find a point in between that, but this is a good those are the half-hour points. This is an hour point, okay? 1 o'clock, 2 o'clock, 3 o'clock. 3 o'clock's right there, in a irrational 3 o'clock, right? And measured vertically. So that's what we're going to do. We're going to roll this circle on the ceiling, you see, so it will roll a full pi radians when it gets to be the green circle. Meanwhile, we'll take the green circle right here and we'll roll it on its ceiling. Okay, it's got a ceiling at y equal 1.91. That's 2 times 3 over pi. Okay, and it's going to be rolling from the right to the left, opposed to this one. The two are going in opposite directions. Okay, and it's doing it on the 1.91 ceiling, and the contact point here goes from here, which is 6 over 2, down to 0. Okay, 0 is right there on the abscissa, the x-axis, if you will. Okay, This one here goes right to left, and it goes from x equals 0, rotating on this circle, on this ceiling right here, and ends up where this one started. Okay? And the reason we're doing that is because I want to see the full structure of the Huygens pendulum, for one thing, but also just get an idea of the geometry of this marvelous curve, the cycloid. So much a part of our life. Every time you throw something through the air or something takes off into space, if it's a rigid body, pieces of it are making cycloids. And in some cases, perfect cycloids like this one, as opposed to prolate and oblate, which you can also construct using this procedure. But we're just going to do the what's called the right cycloid. Okay? So the next tick of pi over 6 is pi over 3. So you just move the circle over to the next division and then see where it intersects pi over 3. Okay? So we've done 1 o'clock, here's 2 o'clock, then we still have to do 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock, and we'll have those points of this cycloid, but this cycloid is going the other way. Get the picture? Okay. Well, you will after you do it. This is one of those things where you can, watch somebody else do it. Say, that's nice, and then walk away. What? You got to do it yourself. Okay? Now, I've done this in class on the board many times, and I can show you pictures of that, and of course they all have little errors, and it's much easier to do it on paper than it is on the board. This one requires a little bit of skill to get it precisely right. Graph paper sure does help. Newton didn't have that. He had to make his own. So here you're seeing those points that we need, okay, that we can make. And they're real close together where the thing starts. These are real close, and then they spread out, you see. So it gets to the point where you really want to have more precision down at the bottom of the cycloid. But the bottom of the cycloid is very flat. Where it really goes crazy is right there. And this one goes crazy right there. And I'm going to, explain a little bit about that as we go into the algebra of the cycloid a little bit. We're also going to do some of this stuff algebraically. But just to give you an idea of what it is that this thing looks like after you've taken away a lot of the garbage, there's just the raw first 2 steps at this precision of pi over 6. There's a sort of a finishing of the thing. And here's what's really cool. When you draw a line between a red point and a green point, you got a tangent. And we're going to play with those. The geometry of those tangents is very interesting. Whenever you draw a curve and then draw a tangent, and then stop the tangent at the radius of curvature, and you have to understand that that is the radius of curvature of this cycloid at that point. Just imagine you're holding the string here, and I go like this and make a little bit of a circle, right? That's the radius, isn't it? So this is a circle that osculates to this cycloid curve. If I were to finish that circle, I didn't bother to draw it because enough lines on this thing already. But you see that I'm getting a very short radius in here. And if you go halfway, you're getting an even shorter one in there, right? And finally, at the very last instant here, you see, the radius is getting finally to 1 pixel, right? If you're just a little fraction of a pixel below the thing, you're talking about something that has enormous curvature. When you look at the cycloid, it looks like it just gets more and more curved as I get up here, but then it just sort of straightens out. No, that's not what happens. At the last thing there, it takes its finger and just really bends the heck out of it. Right? And you can see that by this construction. So this is something that lets you see the cycloid like most people haven't seen it. And it also makes sense out of the algebra for this particular problem. And the problem we're talking about is Huygens pendulum, another anharmonic, what would you think be an anharmonic, but it's just the opposite. It is going the other way and being very harmonic. Now, if I just look at this point right here, the curvature for that and the radius of curvature, I'm actually holding the radius of curvature for this cycloid at this point, okay? Obviously, as I go down to other points, the radius gets shorter. Not much shorter at first. It goes from this length right here to this length right here. Not much of a change, okay? But as I continue, this one isn't much of a change either. The cycloid and this circle that's in gray are indistinguishable at this resolution until about here. I can see a couple of pixels coming out, and then it sort of goes rather quickly up to about 20, 30, 40, 50, 60, maybe 100 pixels right there between the circle and the cycloid, okay? So the cycloid, meanwhile, is getting kinkier and kinkier and kinkier, finally infinitely kinky right at that point. Beautiful. Okay, this is, you know, this is the guts of the cycloid. And it's got to have a friend to work. And that's what's interesting. Whenever you take a curve and unwrap a string and make it always the radius of curvature, which you will do automatically, right? As I just unwrap a string from any curve, okay? That's called the evolute of that curve. And it used to be in every calculus book that you had to calculate the evolutes, okay? Kind of ugly formulas with 3 halves in them. Google it. You'll see pages of algebra for the evolute. But the inverse of that is to take any curve, erect normals at each point, sort of doing the same thing, right? That's called the involute. This curve here is the involute of that one. Now the cycloid is unique in that it is its own evolute and its own involute.
So
Involute. This is spelled I-N-V-O-L-U-T-E.
So does it mean that if you draw a tangent to a point of the evolute and a tangent to a point of an involute, they would be at right angles to each other?
Well, it obviously has to be,
Okay.
right? Because, you know, I'm not moving this point very much at all when I move this, right? I move this one just a little bit. You wouldn't even be able to see the motion on this one. So you're right. That is going to be perpendicular to the radius because it's part of a circle that is the circle of curvature for that point of the curve. That's going from this curve to this one. That's called the involute process. Unwrapping the string just straight away from a point is an evolute. And of course there's all sorts of evolutes. I could start here and make an evolute, start here, make an evolute, start here, make an evolute. We're starting a very special place on the cycloid to make this evolute. Parabola has interesting involutes and evolutes. It's really an amazing bunch of geometry that we just threw it out of the curriculum. Trash can for all this beautiful stuff. Well, you miss a lot of physics when you do that. Okay. Well, we've got just a little bit of time to talk about this, and I'm going to go fairly quickly through this stuff that you should read. Now, I am pulling this from Unit 7. We're getting close to the end of the course here, and I'm now calculating what it is we won't be able to cover, so I'm taking the things that I think you need to know in order to do just, you know, basic, well, pass the qualifying exam, but also, you know, have a basic understanding of Unit 7, which is calculus of variations. We've already done a little bit of that. I've been pulling from Unit 7, sort of piecemeal here. But this idea that a cycloid is a brachistochrone, a minimum time curve for a particle falling in a uniform gravitational potential, but being constrained to that kind of curve, or some other curve that isn't a minimum time curve. So you can just pick 2 points, and you can put a straight line between them, and you know, if the straight line isn't completely flat, you're going to get, you know, a reasonable, very short time to have the ball roll down a straight line. Another possibility would be a circle, okay? The trouble is I can't necessarily make a circle that will start here and go through this point. With cycloid you can. You just rescale it until it fits. That's the thing about a cycloid, is it has that oddity. But, you know, I could just make any old curve coming down here, and as long as the thing didn't go above where I put my finger and make the ball roll back to me, I would have, you know, some time, it takes some time to get down here that would be always, according to what we're going to calculate here, shorter than what it would get if I put a cycloid between these two. Now, if I go real far away, I've got to put a cycloid that does this kind of thing. That's kind of screwy, okay? But if I'm in the range of 2 pi times this distance right here, I can find a cycloid that'll, you know, might come down and then come back up again, but it will be the shortest time. And that's kind of surprising. That is really kind of surprising. Okay? So this is a little bit more of a calculus problem than the ones that we've been doing with straight line trajectories through tunnels in the Earth, in the sophomore physics Earth. This is a little bit more complicated. And in fact, if you want an A in this course, you should find the inside of the crystal cone in the harmonic oscillator.
Inside, what is that?
In other words, what we already found that we could do better than 43 minutes by a particular angle, right, of straight lines inside the Earth, right? That was the hard part of that particular homework set, right? Is to find that, okay? This took 43 minutes. This was very quick, much quicker, right? And then you make it deeper, then it goes back to 43 minutes. But you can beat 43 minutes at a particular angle. Now, there's a curve between there, right? That's hyperchrysticone. Okay, what is that? Well, as you can see, the algebra for this one is already fairly complicated, as we're going to see. Okay, if you haven't been through this, you should look at it. But anyway, you think it's going to be easy because energy conservation immediately gives you the velocity due to gravitational field 2gy. I'm going to fall a certain distance y. My speed has got to be, no matter what I'm doing in x, equal to the square root of 2gy. Okay, so that's the velocity along the arc of the thing that we're claiming to make a precursor cone out of. So we're going to have the integral of dt, and that's ds over the square root of gy. ds, of course, is dx squared plus dy squared. I'm going to take the dy out of there, out of the denominator, okay, and leave me with 1 plus x derivative of x with respect to y. Okay, so this is an integral with respect to y that we're minimizing. This is calculus of variations when you do that. We've already done some easy examples of this, sort of generic examples of this. But here's one way to solve that problem. You see, the Lagrange equation for this integrand, treating this thing as a Lagrangian, I call it a pseudo-Lagrangian because the real Lagrangian was an integral with respect to time. So y is like time here. Okay, but don't confuse that. I'm just using the language here. There's nothing else. So, but I do have a pseudo-momentum here that is constant because the partial derivative with respect to x dot, that's x with respect to y here, so we call it prime, okay? And here's the definition. X prime is dx dy, and that of course is 1 over y prime, which is dy dx. We're talking about the slope here, when we do this thing here with x prime, okay? And I'm taking the partial with respect to that, assuming that that's the variable that defines this integrand, this pseudo-Lagrange integrand, okay? So I got to do this. Already I got a little bit of algebra here, right? This is something that is constant, okay? But still, it's a differential equation. It's going to be simplified. Put the y prime in, you make that y prime squared plus 1 instead of the inverse thing. So, what we're going to do is we're going to change variables from y, which looked good because it was constant, but we're going to use that constant and get it into velocity. Now remember, velocity squared is 2gy, and that means that dy is v dv over g from this relation here, and then y prime is going to be dy over dx. That's dv dx times v over g. So it's a v dv differential, but d derivative, I say v derivative of v, that's going to be the thing that we have to worry about. So this thing is constant. Here are all the different ways to write it. I'm going to skip over a lot of parts here. This becomes this, okay? But finally you can break this down so that you do get an integral that you recognize that you can do analytically. Very classic sophomore physics, sophomore mathematics, calculus 1 integral, okay? And the substitution involves an angle, and that's the way you get the polar coordinates of the cycloid using the calculus of variations, okay? So I go ahead and do that integral, and I get an x equation, and I get a y equation for the cycloid that we've been drawing with ruler and compass. And you can see all it is something that rotates sine and cosine, but one dimension translates. That's all a cycloid is, right? Okay, that's nice. All right? Now, interesting linear dynamics. As I say, I'm going to go through this fairly quickly, but the extraordinary properties that go with this thing because this pseudo-momentum, and I, again, caution you against identifying momentum, but when you do some problems, you can see that there are relations that are kind of interesting. But this thing being a constant, okay, makes for some interesting facts here. I'm going ahead and work the velocity equation now. It comes out very simple, okay, involving, now we've got two ways to coordinate this thing. I can either use phi, or I can use, the phi is 2 theta, or I can use the half angle, okay, which is theta. Okay, so those are the two angles that sometimes one's more convenient than the other in both the algebra and the geometry discussions. Okay, but anyway, a circle that starts at phi equal pi. This is phi and theta 0 at the bottom of the thing. But if I start right here, you've already seen the simulation for that. What we're going to get is rather amusing, but we have to get it algebraically, you see. So this is one of those cases where the geometry is easier than the algebra. In any case, this constant, 1 over px, which is, I'm just calling that A, because it was the amplitude of the cosine that we had substituted. This thing actually relates to arc length. The actual arc length, which is the integral of v dt, the velocity dt, is this thing, which is a very nice effect. It's just 4r sine of the theta, the half angle. Okay? All right. Now, curvature geometry. Okay, I've already mentioned the curvature, but this is dual curvature here. Arc length S indicated by segment HH. Okay, now what I'm talking about here is a segment of this thing that's a length 2h, which is 4r sine theta. Remember the formula we just derived, this works. But here's H prime right here, and here's HH. The segment HH is right here. Okay, see. This is precisely the length of the unwound string between the points M prime and M double prime. Okay? And you can see what we're doing. We're unwinding the string. The string, you know, starts here. Okay, very nice and flat. This thing comes out of this horrible curve right here, but immediately gets adapted to something that looks pretty straight, follows itself down to there. Okay, and then continues up to the top here to make the rest of this cycloid using this one as an evolutor. It evolutes from this one. Okay? Meanwhile, this one right here has an involute, which is right there. Okay, and so they play with each other and have the same kind of curve. And it's always a circle rotating on a ceiling. So this is the geometry we just did, but now it's algebratized. Okay, so we have these segments, H prime, H prime, this thing of length 4r cosine theta. That's this other one right here. Okay, that's unwinding off of the middle cycloid to make the lower one. All right, but do you see the Thales construction in there? This one's a sine theta. This is a cosine theta. That has to be a right angle because it's in Thales' circle, right? So there's your sine and cosine right there. And the cosine, of course, is showing up down here. Isn't that cool? So these are detailed of that stuff we saw in the simulation of the cycloid. Okay? Now, as I pointed out, the curvature, radius of curvature of this thing at points M prime and N prime is determined by these string lengths, okay, and unwinding as they go, okay. So everywhere here we have a circle. This is the biggest circle you'll ever get. There's a circle sort of almost to the end of the cycloid. It's still pretty big. You see, that's the circle of curvature right there. See the string, right, that draws that circle. Okay, I didn't do that very much in any of these drawings because there's so many things on them already. It makes it cluttered. But as these roll synchronously, you see this. And as the M point approaches the top, okay, the curvature becomes infinite. That's what I've already said, but there's the algebraic statement of it thing. So this thing is showing these effects that I've already pointed out in the ruler and compass construction. All right. Now, here's the thing that we've already talked about for Huygens thing that he discovered only just before he died. The cyclic path has a unique ability to guarantee the same frequency for any amplitude, starting amplitude of oscillation. From just having a thing that's very much like an ordinary pendulum at the bottom of the cycloid with that big circle, okay, to going all the way to that singularity of curvature right at the ear, the tips of the ears of the cycloid. Anywhere you start in between those two, you're going to get the same darn frequency. And that is being worked out here. And I'm going to ask you to do it another way, but this is good enough for government work, right, what we've got here. It's kind of like what you most find in mechanics books that go as far enough to discuss this. But the full period is what we're deriving here, and that's a thing. So here's a regular pendulum whose frequency gets slower and slower, and the period longer and longer as we go to higher and higher amplitude. Only in here do we have cosine waves that have the same frequency to within a few pixels, and then it just breaks. Any orbit out here is really slow compared to the orbits that are in the little region that's so good at keeping harmonic motion. Whereas this one always comes home on the axis at the same quarter period. And if you go to the limits where the curvature is enormous, so that you get a phase diagram that's almost a rectangle, that's the sawtooth here. As I approach infinite curvature right here in my space-time graph, I am getting the motion that is absolute constant at the top, and then boom, makes up for it, and then comes back absolutely constant speed. So those are the things that I wanted to show. Okay, now we've got just about 3 minutes here, regular time. We may go a little bit over on this, but I want you to make sure for your qualifying exam that you can do this sophomore physics stuff. But sophomore physics should learn it this way too. This is a cycloid doing a beautiful thing. But I'm out in space and I've got a lever here, just a big meter stick, okay? And I take a hammer, okay, and I hit it, that's H for hit point, from the center of gravity. I hit it, okay, and send it flying forever in space. Okay? So here's snapshots of it at pi/6 intervals, roughly, going, pirouetting through space. And you'll see that it makes another cycloid halfway through the cycloids that are actually the trajectories. And that's the green one right here. This point right here is the magic point that makes a perfect cycloid, the not perlate, not curlate cycloid. Other points on this rule, like the blue one's most extreme, the blue one makes a curlate cycloid like that, and we saw this with our magnetic orbits. Most of the time it's either curlate, or here's a yellow one that's prolate. It's almost a sine curve. Now later when we do our waves and phasors and lines, you'll see cycloids being made by them too. And the low amplitude ones will just look like a cosine wave. But the higher amplitude ones will look like cycloids, approaching the, when the wave is breaking completely, a normal cycloid. And then they will, if they could continue doing the weird stuff they do, make a curlate one that actually has a loop in it. All right? So this is, I think, rather amusing, to say the least. Okay, so here's another one. The red and the green are on a circle that we call radius of gyration, center of percussion circle. This is the radius of gyration, the location of this point, or this one, if I were to do the inverse, is the center of percussion. So these are things that
Dr. Harter,
we need to calculate.
In which unit have you discussed this problem?
Pardon?
In which unit have you discussed this problem?
Oh, 2 units. Unit 1 in chapter 11, I think it is, and then good old unit 7. Unit 7's got lots of nuts, and unit 6 too, actually. So, but go back and look at 1. I'm going to just redo the stuff that's in unit 1, chapter 11. Okay, and there's pictures like this there. The idea is that when I hit that stick, I do 2 things that are of interest to a physicist. First of all, whatever impulse I actually felt in that hammer, it comes into the stick and as momentum pi, linear momentum pi. But while I'm giving it linear momentum around its center of gravity, I'm giving it angular momentum, which is that momentum times h, the hit radius. Okay? Now, having done that, there will be a magic point on there that doesn't move at first. If this is a baseball bat and that's a ball coming in at 90 miles an hour, and you're holding it here, you will not feel it. It's called the sweet spot on the bat. Now, tennis racket is the same way, except you have a lot more lenience and you have a flexible netting that doesn't give you too much of a punch to your hand in any case. But if you hit the sweet spot of a tennis racket, it's a nice feeling because all the power, you feel like you could just be holding onto your tennis racket like that. You should be able to play tennis with 2 fingers. That's the way to learn how to hit all of this physics that we've been doing here. So you should be able to hold that point with your fingers, because the only thing that's going to happen is it's going to start to pull it along the shaft. Just the opposite of what you should be doing when you're hitting. When you say pull the sleeve off of a tennis racket, that's when you're giving it the most energy. This is the inverse of that, where the energy goes boom, and you don't feel it here. So what's happening is the translational momentum is just being canceled by the angular rotation, you see, at that point. Okay? And that's what this is all about. I'm going to go through it very quickly. You should read it on your own. Do it your own. Try working this out without looking, because there are going to be qualifying exam problems very like this and quite often. Resulting angular velocity omega about the center is the angular momentum divided by the moment of inertia. In this case, a stick, it's ml squared over 3, where L is the half radius. Okay? That's just integral of mr squared, really. So That's an easy one. Sphere's got the 2/5 mr squared. Anyway, there's the omega over I, okay? And that's h times pi, angular momentum is h times pi over I, okay? And for the stick, these are the actual numerical, start to be numerical results, okay? Now, 1 point P, center of percussion, is on the wheel where the speed, P omega, due to the rotation, just cancels the translational speed, V center. Now, what's that going to be? Well, that depends on the total mass. Okay, V center, P omega, that's got to be equal to PH pi over I. Okay, and it's pi over M, it's got to be that. Okay? So I can say that if I multiply through by inertia, kill the pi, I've got I over M equal PH. That's the main result. Okay? Or P equal I M over H. If you want to find out where P is, you know where you hit it, this is the thing to calculate. Because you got to know the inertia and the mass. Actually, you don't have to know the mass, you just have to know the coefficient of the inertia, R squared. All right? So P follows a normal cycloid made by a circle. That's this point, this is where it goes. That's a perfect cycloid right there. Okay? Meanwhile, this one also follows a cycloid that hits the thing down here halfway. That's part of what I call the Zamboni problem, which you'll get, I think. Either I'll get it or I'll just give you the thing with the answers. Now, okay, the percussion radius, this L squared 3 over H is, of the CO point, has no velocity just after the hammer hit. We talked about that. Okay, here's a practical pull haul application. Set the bumper height so the ball does not skid. In other words, make that the center of percussion. You've got to adjust the height to do that. Okay? We're going to use this formula, okay? And we want to ask, should the bumper, where should the upper height H be set to make the ball contact point C the center of percussion? In this particular diagram, I'm showing the percussion center way up here, off of C. Okay? That ain't going to work. That's going to be a lousy pull table. Every time the ball hits, it's going to waste energy skidding. In this particular case, when it gets hit from this side, it's going to turn this way, and this part is going to move and skid that way. It's going to go right here, this point. It's going to slide a little bit that way. Okay? So that's too high for P. On the next one, okay, supposing that this is that value, okay? In this case, the P is below the contact point, and the ball will skid this way when I hit it right there. Okay? So the part that we want is right here, where P and C are the same point. So we got to set the P equal the radius of the ball. Okay? And here's P, so bingo. I've got to set the hitting distance so that that works. I'm just using this equation right here.
Dr. Harter?
So I got to do inertia over MR. That's all you got to do.
When you say set the bumper height head so that the ball does not skid, like the ball should hit the wall and it should rebound.
Yeah, it comes up, hits the ball, and literally that's the motion it will do without any skidding. In other words, if a lever on a truck were to come up and hit the wall, right, and the lever had this kind of inertia, right? Okay. Now, for a stick, that's obviously a different height, but for the ball, it's going to be what we get by using this equation. Okay? So I would drive the truck up here and go bang, and it wouldn't kick me. I'd be standing back with this post, right? And all the thing would do is start to rise a little bit for me, right? Whereas if I did any of the other settings, the thing would hit me in the balls and I'd be out of here. Okay? That's what you want to do, is make sure that this part does not kick back. Okay? So here's the answer. Okay? 2/5 MR squared over MR. It's 2/5 of R. That's how much I've got to get to H. 2/5 of R. There's R. There would be 2/5 of it. Okay? Well, it's 2/5 plus 5/5. That's the end of the thing. Here it is. R plus H is 7/10 of 2R. So this has to be 7/10 of this. Now you can go check your local pool table and see, you know, if that makes sense. Okay, as the next slide says, that's all, folks. But I think it's enough. Maybe a little.